we can look at another problem here. At a constant pressure of 100 kilopascals, 100 kilojoule of thermal energy is added to a piston cylinder system. During this heat transfer, the piston moves so that the initial volume increases from 0.5 meter cube to 2 meter cube. If the initial temperature of the system was 330 Kelvin, determine the change in internal energy, the final temperature. We have no information given about the piston. So, we are going to assume that the piston is massless, or we can assume in this case that the piston cylinder arrangement is horizontal, so that we do not have to worry about the piston itself. So, at a constant pressure of 100 kilopascal, so this is a constant pressure process. So, we have 100 kilojoules of thermal energy which is added. As some pressure outside, the pressure inside remains 100 kilopascal all the time. So, the initial volume is 0.5 meter cube, the final volume is 2 meter cube, the initial temperature is 330 Kelvin, the pressure is known, we are asked to find out the change in internal energy and the final temperature. So, we want this and we want this. So, we know that initially P, V and T are like this. Finally, we know pressure and volume. So, if we assume that this was an ideal gas, we can write this and dividing one by the other, these get cancelled. So, we are left with this expression. So, we should be able to find out T2 from this. Pressures also are the same. So, these are cancelled. So, that is T1 into V2 by V1. So, T1 was 330, V2 was 2 meter cube and V1 is 0.5. So, this is 4. So, that is 330 into 4. So, that is 1320 Kelvin if I am doing the multiplication correct. What we are looking for is also the change in internal energy, which is given as mCV into delta T. We do not know what substance this is. We know the final temperature. We also know that there is some work being done in this case. What we are also given is that the heat transferred is 100 kilojoule, which is added. So, we know the heat transfer, which is coming into the system, it is positive, heat transferred into the system we know. We know that the volume is expanding, volume is increasing, that therefore, there is work done. We do not know what is CV and we do not know what is M. So, we do not know what is R either. So, we cannot use this formula directly, but what we know is this, and what we can find out is the work done. There is only expansion work done. Work done in this case would be given as integral P dV. This particular case, the process is a constant pressure process. So, we can get this as in P into integral dV. So, P is given as 100 kilopascal. So, it is 110 power 3 Pascal, and dV is 2 meter cube minus 0.5 meter cube, that is 1.5 meter cube. So, I have 1.5 into 100, which is 150 into 10 power cube. So, that is 150 kilopascal is the amount of work which is done. The work done is positive because this is expanding. Sorry, I have written this as kilopascal when I meant to write kilojoule. This is work in kilojoules. So, what we see is this is the amount of work which is done. So, now if we write the first law, so we have dE is del q minus del w, or in the integrated fashion delta E is q minus w. And in this case this piston cylinder arrangement itself is not moving. So, there is no change in kinetic energy or potential energy of this. So, this is further equal to delta U, which is what I want to find out. So, delta U is essentially q minus w. So, I have q which is 100 kilojoule, I have w which is 150 kilojoule. So, I get this as minus 50 kilojoule, which means that the final internal energy of the system is lower than the initial initial internal energy of the system. So, this system is losing energy during this process. So, it is getting some amount of heat, but it is doing more amount of work and it is using up some of its savings of energy in doing this work. So, that is essentially what we see.